anyways, thank you for that. Thank you for reminding me to record. Exam covering these sections at this day, this time, in this room. And not covering 1.6, though don't be too worried about that because we'll try and get to it at the end of the semester, and even if we do completely miss it, it's not a super critical section. Okay, so all that out of the way. Oh no, one more thing about the exam. I don't remember how much I've been keeping up with giving you guys review problems. I told you I would do that, like in addition to your homework assignments in WebAssign, that I would give you problems to try from each section that you can kind of compile at the, like on Friday when we're done with everything and use this as a review. So here's some problems to look at. Now, if I've already given you some, my apologies for that. Just add these to that list. Though I feel like if I've already given you some, that these might already be in those lists. But these are the ones that I wrote down to mark for review, specifically for this exam. And then 1.5, 1, 2, 21, 53, and 63. So section 1.5 is going to be, there's going to be a bit more going on there. So yeah, so problems 9 and 10 from 0.4, that's the radical and rational exponent stuff. Just one problem from section 6, so that's just a factoring problem. This is about the coordinate plane, so you can expect graphing points and distance formula and midpoint formula. 1.2 was about graphing equations in 2 variables, but it kind of like culminated in that circle stuff and also finding x and y intercepts of stuff. And when I say stuff, I mean like equations that have 2 variables, x and y. So this is a circle problem because that was kind of like the big thing in 1.2 was learning to make tables of values, finding x and y intercepts, and also circles, dealing with that circle equation with its center and radius. Okay, then today we're doing lines, whole bunch of stuff to talk about in lines, but these are the 2 problems I chose there. And then we'll talk about these later sections, when we get to them. All right. Devin can't join. 1 second, let me send him an invite or call him. Sorry guys, 1 second. I'll make sure I get Devin sorted out here. Okay, hopefully he sees those. Or maybe he'll be able to join later. I don't know what that might be about, but okay. There's those problems. Actually, I'm gonna keep that. Okay, so let's go into section 1.3, which is lines. Okay. I'm going to go through this pretty quick because this is pretty much all going to be review for you. So we're going to be looking at lines. Now in equation form, we should know that they look like y equals mx plus b, or maybe if you write them in standard form, sometimes you'll see them written this way, ax plus by equals c, something like that, where sometimes you'll see the a's and b's capitalized, sometimes not. It just the point is that this is just 2 forms of a line in equation form. This is 2 lines in equation form. Now on a graph, we like to talk about the slope of the line. So on a graph, if I graph a straight line, then I'll just arbitrarily put there's the line. Then I can talk about, on the picture here, I can talk about the slope of the line is, when it's written in this form, we call it m. So when y is explicitly solved for in this equation form, y is explicitly solved for, meaning y is all by itself here on this side of the equal sign, then the number attached to x via multiplication is going to be the slope of the line. But what does that mean in the picture? What does that mean in the picture? Well, slope is a measure of, it's a ratio, a measure of how much the line is growing vertically versus how much the line is growing horizontally. So how can I tell if I pick two arbitrary points here and up here and call the first point x1 comma y1, which is standard notation. We've looked at that before, right? Like putting little subscripts on the point. So that's x sub 1 comma y sub 1. And let's just call this point generically x sub 2 comma y sub 2. So just naming them. Then if I said that slope is supposed to be a ratio measuring, so first of all, ratio means fraction, measuring how much it grows in the vertical, how much vertical distance it's covering between 2 points. Well, that's going to be this distance here, right? Vertical distance between this point and this point is just how far up did this point go from this one. And how do I find that? Well, of course, that's just going to be the difference in those two y values. If this one is at a y value of 3, and this one's at a y value of 5, how much did it grow vertically? You would just subtract to figure that out. Okay, and then right here will be the distance that it grew in the horizontal direction. So if the x value here is at 1 and this x value is at 4, then how much would they have, what's the distance between them? It would be the difference, right? A 3 in that case, but in general, it's the difference. Okay, so the slope of the line is just how much it's growing in the y direction versus how much it's growing in the x direction, given 2 points there. All right. Now we can say some more about this. Some things, here are some things to note. About the slope formula. First of all, it's equal to 0. It's 0 if the top is 0, right? That's how a fraction works. If the top is 0, then the entire, like 0 over 5 or something like that, then the entire fraction is 0. So it's 0 if that top, y2 minus 1, y1 is equal to 0. What does that mean? Well, that means y2 is equal to y1, okay? So for a line with a 0 slope, all of the y values are the same. What does it mean if all the y values are the same? It means the height is all the same everywhere along the line. It's not growing or shrinking vertically. It's flat, right? This means, and what do we say? How do we describe flat? The line is horizontal. Okay, and one more point, continuing this point rather, one more note is that lines that are horizontal lines are of the form, what does the equation look like? Y equals, and then some number, just some generic number there. I could say like 3, and that means it would be a flat line at 3. I could say 0, and that would mean it would be a flat line right along the x-axis. I could say -2, and that would mean it would be a flat line at -2. So I'm just going to say equals a number here. I don't want to confuse you and put another letter name there, so we'll just say a number. Okay, another note about the slope formula, that's fine, is it's undefined. Now, how do we have undefined in a fraction when the denominator is 0, right? So it's undefined if x2 minus x1 is equal to 0. If the denominator is 0, that would make the slope undefined. But what does that mean? That means x2 minus x1 is equal to 0. In other words, that x2 is equal to x1. If all the x values are the same, so if I take a point on the graph and then I take another point, but its x value isn't changing, that means the line is just going straight up and down. It's stuck at some x value. That means, or this means, the line is vertical. And then lines that are vertical are of the form, so I'll say it this way, vertical lines are of the form. Now, last time, horizontal lines are of the form y equals a number, so you may have already figured out vertical lines will be of the form x equals a number. Okay. Alrighty. So that sums up a couple of those weird cases when you have horizontal and vertical lines. So some quick examples of these. Draw them over here. Let's see, I've just got just a quick coordinate plane. Let's not worry about putting tick marks all over it. Let's say if I had this line down here, and let's just say that's -1 right there. Then I would describe this line. Well, if it's horizontal, that means all its y values are the same, right? It's not growing vertically. So it's going to be y is equal to -1. This whole line is just described by this equation. This equation here. It's a special case. It's a special case of the y equals mx plus b thing. And then here, for a vertical line, say I had a line, here's x and here's y. Say I had a line like over here, and let's just pretend that that's at 2. So 1, 2 there. Then this line would be x equals 2. That's it. That little equation describes this whole line. And we say that this red line here, this horizontal line, has 0 slope because it's flat. And this line here, a vertical line, has undefined slope. Cool. All right. So those are the special cases. So now let's get back to working with the generic y equals mx plus b, not just the special cases. All right. So okay. So let's just quickly recall y equals mx plus b, that is the slope, slope, and b is the y coordinate of the y-intercept. Okay, so that means if I draw some line, all right, so if I draw some line here, going through here and here, like that, going through the x-axis at -2 and the y-axis at +3. And I say, what is the equation of the line? You should be able to write down the equation of the line. What is the equation of the line? If you have a picture, all you have to do is figure out what the slope is by counting the vertical distance between 2 points that you know about and the x distance between those 2 points. That'll give you the slope. So to find the slope, I'm going to count the distance, the y distance between these 2 points that I'm pretty sure about, right? They definitely go through that point and that point. So from here going up, that distance is, it's going up 3. So I know that the m should have a numerator of 3, the rise, right? You may have heard slope described as rise over run. The rise is 3, and it goes horizontal 1, 2, right? 2 positions, 1, 2. So the slope here is 3 over 2. And by the way, what's the y-intercept of this line? It's 0, 3, right? That's the y-intercept. The b value in my equation, that letter b, is the y-coordinate of the y-intercept. So in other words, it's the 3. So my equation here is 3 halves x, 3 over 2x, plus 3. That describes this line here. So to find the equation of a line given a picture, it's really a matter of finding 2 points, finding 2 clean points that you see and counting off the slope, rise over run, and then also just kind of noting where the y-intercept is and tacking that onto the back. And of course, slopes can be negative, right? If it goes, down and over, down and right, then that's a negative line. You can have a negative slope. You can have a negative y-intercept too if the line's down here. Yeah. Okay. Can we write this equation? Write the equation for the line. In standard form. So what we've written it in is slope-intercept form, but let's write it in standard form. And remember, standard form is the ax plus by equals c. Okay. How can we do that? Well, if you have it in slope-intercept form and you want it in standard form, it's really just a matter of getting the constant term, the 3, by itself. That kind of describes what's going on here. But what we would really say is we would take, let's see, we would start with y equals 3 halves x plus 3. If I want to get this number by itself, in other words, I want the x's and the y's on the left-hand side, then I'm going to subtract the 3 halves x from both sides. So y minus 3 halves x is equal to 3, just subtracting 3 halves x on both sides, right? It just scoots it across the equal sign. There it is. The 3 is still positive. And I'm also going to try to get rid of the fraction. If there are fractions here, we want to get rid of it. And how do I do that? By multiplying everything by the denominator. Okay. So that means I'm going to multiply this entire equation by 2. That's effectively going to cancel that 2 out. So notice I'm multiplying everything by 2. That's going to have, the purpose of this is to cancel this out, but it's going to have an effect of doubling the y, making this just a 3x, right? Because the 2 cancels with that 2 in the denominator, and then of course the 3 turns into a 6. This is the proper standard form of the original line that we wrote down, y equals 3 halves x plus 3. So there's just one problem. That this is just a notation thing, getting from one form to the other. Just a minor thing, it's just manipulating the equation. Get the x's and y's together over here and then get rid of any denominators. So we can get a nice clean, no fractions in our standard form there. Okay. Now, when is standard form useful? Well, standard form is useful when you have a When is standard form useful? Why would we ever care about standard form? It's useful for finding x and y intercepts, I suppose. Though really the other form's not terrible either for finding x and y intercepts. So what do I mean by this? If I wanted to find the x-intercept of this equation, I set y equal to 0, which effectively just zeroes that term out, and I just have, 2 times 0 minus 3x is equal to 6, and that's going to be negative 3x is equal to 6. So x is -2, just dividing by -3 on both sides. So my my x-intercept is -2, 0. Okay, and similarly for the y-intercept, you plug in 0 for x, 2y minus 3 times 0. Of course, 2y minus 0 is just 2y. So I have 2y equals 6. So y is equal to 3. Giving me, oh, can't see that, there we go, giving me a 0, 3 for the y-intercept. Now, does this make sense with the picture I drew earlier? Because this is still the same line. And if I look at the picture, in fact, I already noted the y-intercept on this picture is 0, 3, so that checks there, 0, 3 for the y-intercept. And the x-intercept should be at -2, 0, which is what I got here. Okay. So if you're wondering why the heck is standard form even talked about, if the y equals mx plus b form is so much more common and seems so much more useful, well, standard form has its uses, and it's mainly in finding the x and y intercepts. And why do we care about finding these? Well, if you have 2 points, then you can graph the line, right? If I can graph these 2 points, all I need to do to graph a straight line once I have 2 points is just connect them, right? All right, so I know this is like a whirlwind of stuff, but I know all of you guys have seen this before. Yeah, because it's on the EdReady stuff. So that's why I'm going so quick. All right, let's do a classic problem here. Find the equation of a line that passes through, I'm going to give you 2 points. You should probably remember this kind of problem. Find the equation of a line that passes through the points -2, 3, and let me think. I don't want to make this too terrible. Hang on, give me a moment. That's 6. Let's see, 15. Okay. So I could just graph these points and then connect them and try to find its slope and y-intercept, but that's not advised. Mainly because graphing this would take some time, especially considering that 15 is pretty big, right? You'd need a pretty big graph. Also, even if you do get it graphed nicely, what if the y-intercept is fractional? What if it goes between 2 of your little tick marks? And then you're like, oh, is that 1/2 or 1/3 or something, So getting a picture for this particular problem is not advised. What we will do is we will find the slope. That's going to be step 1, and then we're going to find the y-intercept. Because those are the 2 parts that build the y equals mx plus b, right? The m and the y-intercept, 0, b, which really we want the b, right? But if we get this, then we'll have b. All right. How do we find slope given 2 points? Well, I gave you an equation for that, right? It's the difference of the y values. So if I choose this as 0.2, you may want to label these x2, y2, x1, y1. Maybe I'll even do that here. x2, y2, just to keep the formula straight until you're comfortable with it. So 15 minus 3, difference of the y values, and then difference of the x values. So I've got minus a negative there. I'll need to watch out for that. 15 minus 3 is 12, and 4 minus negative 2, that turns into a sum. So 6. 4 plus 2 is 6. Reduce, always try to reduce, which thankfully this reduces into a whole number. Okay, step 1 done. That's step 1. Straight up use the formula. And hope that your answer is whole number. It's fine if it's a fraction, right? It could have been 12 over 5, right? But there's nothing wrong with it being a fraction. It's just, of course, the rest of the work is going to be a little bit more difficult. All right, so here we go. Step 2. Find the y-intercept. Where are we in our equation right now? We have y equals, sorry, hang on. My phone is going crazy. All right. Y is equal to mx plus b, but we have 2. So m is 2. So we don't have mx plus b, we have 2x plus b. All right. Why is that useful? Well, because now what we can do is now we can plug in a point into x and y and solve for b. Okay, so we'll take one of these points, -2, 3, or 4, 15, plug it in for x and y, and then we'll just be left with an equation just with the letter b in it, in numbers, and we can solve for b, right? So does it matter which point you pick? No, we were given 2 points here, so it doesn't matter which point I pick. I'll pick this one, 4, 15, just because it doesn't have a negative. You could pick this one, and if you do your math right, you'll get the same answer I do. So 4, 15 is what I'm going to plug in. So that means the y value is 15. The x value is 4. Okay. So 15 is equal to 8 plus b, which of course yields b is equal to 7, subtracting 8 from both sides. Okay, so my y-intercept is 0, 7. But what does this mean for my equation now? Well, I've got b. I've got y equals 2x, but now I say instead of just plus b, the letter b, I can say 7, and then we're done. That's it. Find slope, write down the equation with slope plugged in, plug in a point into x and y, solve for b, write it all down. That's it. That is a classic process there for a classic problem. The problem being find the equation of a line that passes through these 2 points, or through any 2 points, right? Always find slope and then proceed through step 2 as normal, or as I did here. All right, let's talk about parallel and perpendicular lines and the relationship to slope. Okay, here we go. Parallel lines have equal slopes. Perpendicular lines now here comes a weird description, have negative reciprocal slopes. Okay, what does that mean? So just as an example here, well, negative, you know what negative means, but reciprocal is the multiplicative inverse of a number. In other words, flip it upside down. Like, for example, if the slope of your line, so I'll just sub it with 1. So if you've got a slope of 3/2, then the perpendicular slope would be negative, and then flip the 3/2 2/3. Or as another example, if you've got a slope of 2, then the perpendicular slope, or a line with a perpendicular slope, would have a slope of negative 1/2. And of course, if you start with a negative and then you negate it, then it'll end up being positive. The point is they should have opposite signs and they should be flipped. And how did I get 1/2 here? Well, I understand that 2 is the same technically as 2/1. So when I flip 2/1, I get 1/2. So this can lead, okay, I really want to get to section 1.4. So let me do one more problem. These facts can lead to problems like this. Find the equation of a line that is perpendicular to the line y equals negative 1/3 x plus 5, and that passes through the point. Let me think for a moment. 2, I think 3, so 2, yeah, that's fine. Through the point 2, 2. All right, anytime you're wanting to build the equation of a line, step 1 is going to be to find the slope. Now, last time we found slope. So last time, given 2 points, we found the slope by plugging into the formula because we were given 2 points. Not going to be the case here. Excuse me, not going to be the case here. Here, we're going to use this fact about perpendicular lines. So can anyone tell me what is the slope of our line? So their line, the line they gave is negative 1/3, or rather its slope is negative 1/3. So what is the slope of our line? Anyone have an idea? Negative reciprocal of negative 1/3 would be positive 3. That's it. No need for formula here. And how did I get that 3? It's the negative reciprocal of negative 1/3. Step 2 is going to be the same as it was last time. You write down the equation that you have so far, y equals 3x plus b, and now plug in the point they give you, 2, 2. So y is 2, x is 2, solve for b. That's 6, so 2 is equal to 6 plus b. So b is negative 4. Okay, just subtracting 6 from both sides. So we get y is equal to 3x minus 4. There it is. Okay. Are there any questions about any of the line stuff before we get into section 1.4? Cool. Okay. So that was 1.3. Now we're moving into 1.4, which is solving quadratic equations. So section 1.3 was about graphing linear equations, but really you could also argue that, we could talk about solving linear equations. How would you solve a linear equation in general? Now remember, linear means both of the variables have an exponent of 1. And what does it mean to solve a linear equation? Hang on. So if I have something like a generic linear equation with y explicitly solved for, which is what we're going to be dealing with for the most part, I could say mx plus b, but since I'm not talking about graphing it, so I don't want to use the letter m because that implies that we're talking about graphing. So I'm just talking about the equation part of it. I can say y is equal to ax plus b. And what does it mean to solve a linear equation? It really means, what does that mean to solve the linear equation? So I'll put star. What does that mean? It means to solve the equation, that equation, when y is equal to 0. In other words, to find the roots of it when y is equal to 0. So when we say to solve a linear equation, or just to solve an equation in general, if we're talking about them in this context, we really mean you're setting the entire equation equal to 0, having an output of 0, and you want to figure out how to solve it. And we can solve this pretty easily in general. You just subtract the b and divide by a, so x would just be negative b over a. Okay, so, and why do you've probably not seen this done this way, because why would you, right? Because solving linear equations is super easy. Well, relative to other math, right? Solving linear equations is like one of the nicer things that happens in math. You don't need a general form for it, right? You don't need a formula, right? In fact, the formula probably even is more confusing than the actual process, right? So what about solving quadratic equations in general? So here we're moving on to what about quadratic equations? And what is a quadratic equation? It's going to be an equation in this form. Instead of just ax plus b, we have this form, ax squared plus bx plus c. And when we talk about wanting to solve them, what we want is the x values that solve this equation, similar to how I set up the last thing I was talking about with linear equations. We want to solve for the zeros of it. We want to know what x values can I plug in that yield a 0. Okay. So what do we know so far about stuff here on this left-hand side? What do we know about stuff on this left-hand side? We know how to factor ax squared plus bx plus c sometimes. It depends on the numbers, right? Why is this useful? Like, why do we spend all that time talking about factoring quadratics or factoring degree 2 polynomials? Why we had a whole section on it, right? Why do we talk about that? Why do you do it in high school? And well, consider this problem. Say we have, let's just start off with a real simple one. In fact, one that we've already dealt with. We can factor this left-hand side, we already know, into x plus 3 times x plus 4. Okay, so still, why is this useful? Note that when two things are being multiplied together, as they are here, so this went from like a sum of stuff, like this plus this plus this, but now it's a product of these two things, this thing times this thing. But note that in general, if you have two things being multiplied together, a times b, just too generic, it could be numbers, polynomials, functions, it doesn't matter. If two things are being multiplied together and they're equal to 0, what can we say about these things? What can we say about a or b? Any guesses? we can say that A is equal to 0 or B is equal to 0. Right? If I tell you AB is equal to 0, well, then you say, well, at least one of them has to be 0. At least one of them has to be 0. So why is that? Why am I pointing that out? Well, that's exactly the setup I have here. And if I'm telling you that this is true for any A and B, well, my A, what's playing the role of A over here? This entire x plus 3 thing. So this equation, when you have the product of two things equal to 0, which is exactly what factoring does for us, it takes this and writes it as a product. If you have the product of two things equal to 0, then you can set each of them equal to 0 individually, and you can solve, and you get x is -3 or x is -4 in this case. You can solve the two leftover pieces because they're both linear, right? They're easy to solve because they're both linear. Okay. What does this mean? This means that -3 plugged into this equation yields a 0. -4 plugged into this equation yields a 0. And those are the only two values that you plug into this equation to get a 0. There are no other ones that exist that when you plug them in will yield a 0. These are the only two values that exist for x. When you plug them in, they equal 0. This is already getting different than linear equations because we have two of them, right? For a linear equation, there's just one, right? X is equal to just one number, but here we have two. We have two. It won't always be that way, but in general, you can have two solutions. So this is why we learn how to factor, because it lets us solve the next level of equations, which is quadratic equations. So, with that being said, let's call this example 1. I know I didn't list any examples in the lines unit or lines section 1.3, but that's because 1.3 was kind of a whirlwind of stuff all happening together. So I'll be a little bit more structured here. So let's say example 1, solve, let's say x squared, plus 5x minus 24 is equal to 0 by factoring. So you still have to remember how to factor it. So I'm looking for two numbers such that their product is -24, like maybe 2 and 12, or 6 and 4, or 3 and 8. But their sum has to be 5. So I'm definitely thinking 3 and 8. So there's definitely going to be an x in both of these because it's just a leading coefficient of 1. So I'm not doing the grouping method here. And I'm thinking 3 and 8, but I need one of them to be negative, one to be positive. If the sum is positive, that means the bigger number should be positive. So there we go. Writing x, all of this is still equal to 0. So I've just factored the left-hand side. Now I can use that 0 product property, which I wrote back here in blue. That's called the 0 product property. Setting each of these equal to 0 independently. And I get the two values that you can plug into this equation to yield 0. Okay. How about this? Okay, so we're solving this one by factoring. All right, well, so same process, thinking of two numbers that multiply. I'm just going to go ahead and set everything up here. Two numbers that multiply to give 9, so it's either 1 and 9 or 3 and 3, but they have to add to give 6. So I'm thinking, okay, it's got to be the 3 and 3, and of course everything is positive here, so they're positive. So what happens here? Well, if I split these, I'm just going to have a repeat, right? Just going to have a repeat. X equals -3 is the only solution. So what I'm pointing out is that sometimes quadratic equations can have two distinct solutions. Sometimes quadratic equations can only have one real solution. Sometimes they can have 0, but that's going to be, we'll talk about that in section 1.5. So sometimes they can have 2, sometimes they can have 1. Now, so far, none of this is really super new because all the work being done is honestly just the factoring, and you already knew how to do that. And the rest of it's just kind of like, okay, I get it, split, get it factored, split them, solve each of them. So what about some new well, actually, I said that like I was about to start talking about something new, but I actually want to do one more. That's a grouping problem, just to give you a little bit more practice with that. So just in case you don't remember how to do this. Whoops, I meant to, that's 15. 2x squared plus 11x plus 15 by factoring. Okay, so we look at this and we go, oh, dang it, it's a grouping problem, right? So I need to, maybe I should actually draw the little chart of numbers over here so I don't get mixed up. I need the 2 numbers to add to give the middle term, but the two numbers also need to multiply to give the product of the leading coefficient and the constant. In other words, 30, 2 times 15 there. So we think about this for a while, think about, okay, I've got my chart set up. What is going to solve this for me? And it's going to be a 5 and a 6. So eventually you would get there. 5 times 6 is 30, 5 plus 6 is 11. So then we say 2x squared. Remember, this is the longer process where you can't just jump straight to the factored form. You got to split that middle term, 11. And then you group. Now, by the way, someone always figures this out every semester, that you can kind of just brute force your way through these just by like plugging in and checking different numbers to factor something like this. That's totally legit too, by the way. Like if you like think like a computer and you're like, okay, I kind of know where it should be. Let me just start trying stuff until I get something that works. That's fine. I mean, but this is the more algorithmic way, I suppose, of approaching it. I messed up there, so I'm just completing the grouping method here. So I grouped the terms. I pulled out the common term of x here, pulled out a common term of 3 here. I'm going to pull out the entire, look, this whole thing's common now. That's the point, right? 2x plus 5, 2x plus 5. All right, there it is. So that's a quick review of the grouping method. And now to finish the problem, though, I need to actually solve each of these. This one's easy, -3. What about this one? Well, I would subtract 5, right? So there's a little bit more going on this side. Subtract 5 from both sides, and then divide by 2. Okay, so there's my 2 solutions to this equation. -3 and this ugly fraction, -5/2. Apparently, if you plug -5/2 into this, you get 0. And it's true. You could check it if you wanted to. Okay. Now let's get into what if the equations can't be factored. I know we're almost out of time, but what if excuse me. So what's an example of an equation that cannot be factored? Maybe x squared minus 8x plus 13. There's no way to get, 2 numbers that multiply to give 13 that add to give -8. No, because 13's prime. 1 and 13 are the only choices. It doesn't work. It cannot be factored. Okay. Well, it can't be factored using fractions or integers or anything like that. Okay. So, but as we understand it, it cannot be factored. Okay. So how do we solve it? Or do we just throw our hands up in the air and say some quadratic equations can't be solved? Well, no, there is a way. There is a way. And that's going to come down to the quadratic formula. So last time, or a few minutes ago, I said you don't really have a formula for solving generic linear equations because they're pretty easy. You don't need a formula. Quadratic equations, though, generally cannot be factored. I mean, sometimes they can, and then you solve them that way, the 3 examples we just did. But what if they can't? Then they're too complicated for you to start over every time and try to like where would you even start with this? You know, just plugging in random numbers. So we need a formula. And the formula is going to use something called completing the square. And completing the square is like the bane of every pre-calculus algebra student's existence. Like, it's like synonymous with like pain and suffering for some reason. I mean, well, for the reason is this, that it's hard, and there's a lot going on. So since this course is a little different, and I can't even really like hold you accountable for learning it because you can always just use a different method to solve the equations, we're going to flip the script a little bit. I'm going to derive the quadratic formula for you using the method of completing the square, and ask that you try your best to follow along through that. And once we have it derived, I'm just going to let you use the formula for whatever you want. I'm not going to hold you accountable for using completing the square method. And the reason I'm doing that is because, like, how can I force you to use a certain method on a multiple choice online exam, right? Like an exam on the computer where you don't really, I mean, I would have to collect everyone's work, and that's just a bad idea right now with the pandemic. So that's kind of my plan, is to, we will. So I'm still going to show you completing the square, but not hold you accountable for using it. We will use completing the square, this method that I haven't even told you what it is yet, completing the square, to derive a formula. Formula. I didn't mean to. For a generic quadratic equation. And what do I mean by generic quadratic equation? I mean like ax squared plus bx and then plus c equals 0. And we're going to get a formula for it. You probably already know what the quadratic formula is, or maybe you've seen or heard of it before, but so you may remember that it looks kind of like a lot going on. We're going to build it from scratch, and that'll be kind of the give and take for me, not forcing you to use the completing the square method on, you know, homework problem or test problems, you know. So next time we will start with that. We will derive the quadratic formula and practice using it, and that'll be what we do on Wednesday. All right, so that's the end of the lecture. I'm going to stop recording.